Welcome back to the second part of our tutorial on representation learning without labels. In this part, we're going to be talking about building blocks. So let's just jump right in. You might remember from the first part that we talked about the realm of images and the realm of representations. So images are these impoverished projections of reality, and representations are the observer's mind's eye view of that reality. And in this context, there's actually two processes that are important to think about. One is the process that goes from images to representations. Some people call that understanding. And the other is the process that goes from representations back to images. Some people call that imagination, or the image formation process. Now, remember, we don't have access to the actual real object in this context. And so all we really have to go by are these two processes. Now, there's a whole zoo of methods that people have come up with, so many that we wouldn't be able to cover all in this tutorial. But what we're going to try and do is go over a dozen or so models, looking at what they have in common and trying to extract common components or building blocks that we can use to create new models into the future. So the first component that is perhaps most obvious is the representation or encoder or inference network. So this is a neural network that takes an input X and processes it to produce a representation R. In these diagrams, I'm going to use this shape for X, even though in reality it's probably going to be two-dimensional or n-dimensional. And the representation R, I'm going to draw as something smaller to indicate that we would like it to be more abstract, but it's generally going to be a vector or potentially a very large vector. Now, in designing representation networks, we get to choose several things. We get to choose the size of R, whether it's smaller or larger than X. We get to choose its structure, whether it's flat or if it's interpretable, and whether it's continuously valued or if it's discrete. Whether the shape is fixed or it changes for different inputs, whether it's disentangled or not. We also get to choose the architecture of the network itself, whether it's an MLP or not, whether if it's a convnet or a transformer or an RNN. Now, more generally, the representation network doesn't have to be a network at all. It could be an inference algorithm, and this is what was often done before the rise of deep learning. And inference algorithms vary in terms of whether they're differentiable or not. So neural networks are obviously differentiable, but you might be using search or sampling to come up with a representation R, and those processes might not be differentiable. The algorithm could be interpretable, or it could be a black box. It could be deterministic, or it could be stochastic, meaning in the stochastic case, for a given X, you might get different Rs. Now, the second component that is perhaps obvious to think about are generation networks or generators or decoders. So this mirrors that of the representation network, except now it takes the representation R as input, processes it, and produces an output X prime. And like the representation network, the architecture of the generation network could be an MLP, it could be a deconvolutional net, it could be a transformer, it could be an RNN again. And generally speaking, X prime has similar shape to X, but that doesn't always have to be the case. And you can also step back from neural networks and consider cases where you have an algorithm that's actually producing this output. It doesn't have to be a neural network. Sometimes these algorithms are called simulators or renderers. And again, they could be differentiable, like with a neural network, or they might not be. They might be interpretable. For instance, it could be a graphics program or a renderer, or they might not be. It could be deterministic or stochastic. And we'll see examples of this over the next few slides. Now, if you put these two components together, you end up with an architecture that is very well studied, and that's the architecture of autoencoders. So the idea here is that you take X, you pass it through the representation network to get R, you pass that through the generation network to get X prime. And you train autoencoders to make X prime as similar as possible to X. And typically, this is done with a likelihood-based objective. So you want to maximize the likelihood of the true input X given the predicted x prime. And it goes without saying that these autoencoders can be drawn in different ways, horizontally or vertically, or even broken into two pieces. So here we've got a vertical depiction of an autoencoder. And this figure on the right is from Hinton's famous 2006 science paper, where, for instance, they trained autoencoders on faces. So you have the input face being processed by an MLP down to a 30 units representation, and then being processed back up with the decoder to a reconstruction of that face. Now, autoencoders can be used for a variety of things. Density estimation, that is assigning a probability to each input. Dimensionality reduction, that is reducing this input, which might be high dimensional, to a small number of numbers that you would use to save on memory. Image generation, that is after having trained this, you sample representations and you produce new images. Or denoising, where if you have a noisy input, you go through the autoencoder to get a denoised output. But what we care about for the purpose of this tutorial is representation learning. That is, if I give an input to this encoder and I get a representation, how useful is that? How much does it capture the contents of the image? Now, the intuition with an autoencoder or autoencoder-like methods is that if the autoencoder is successful at reconstructing the inputs accurately, then this representation must somehow encode enough information about the input to do that reconstruction. And the hypothesis is that this representation, therefore, is a good representation. It's going to be a useful representation because it is both concise and accurate. One way people visualize the learned representation space is by what they call latent space traversal. So here, imagine I've trained an autoencoder on MNIST digits, and the representation space I've chosen to be two-dimensional. So R has two components to it. What I can then do is I can change each component individually. I can basically walk around this two-dimensional space and pass the representation R that results in that space through the generation network each time to produce an image. So the 7 is what I would get if I was in the top left-hand side of this space. As I move along that space in different directions, I get different generations from my network. And this is basically the intuition that people use when they sample from these generation networks. They want to show that by moving around the space, they're getting meaningful samples out. Now, what some people have worked on is what they call disentangled autoencoders, where they try to take this vector R and actually break it down into components. So in this example, we've broken it down into 4 components. And they encourage learning to learn components that are somehow independent from each other, or orthogonal to each other, or disentangled from each other. By modifying the loss in just the right ways, you might end up with a representation vector that has these properties. So for instance, what you can do is you can take your representation and you can vary one component at a time and observe what effect it has on your samples. So here I modify R1, and I see that as I do that, it's taking the same shapes and it's moving them up and down. If I modify another component, it's taking those shapes and it's moving them side to side. And a third component is modifying their colors. So the hope here is that instead of having all of these factors entangled with each other in this representation space, you have those factors be axis aligned effectively, which allows you to do this kind of analysis. Now, another obvious modification you can make to the standard autoencoding architecture is to make the representation and generation networks sequential. Whereas before we just had an MLP or a convnet that was producing R, and then an MLP or a convnet that was producing X prime given R, we can now replace them with RNNs. So the idea here is that you process X to get the first R, that produces an intermediate reconstruction or canvas. And then you repeat this process, creating refined Rs and refined canvases until you have your final reconstruction X prime. Now, obviously, one of the benefits that you get from this is that you have a more powerful encoder and a more powerful decoder in terms of simply the number of layers in your neural network. But there's another reason why you might do this. So in this paper, Gregor and co-authors, they took an architecture of this kind, and what they did during training was train as I described, but at test time, what they could do is they could limit the number of times the representation network could look at the input to produce the reconstruction. And by limiting it in this way, what you can do is you can control the number of bits effectively that the representation network can send to the generator. So these Rs are sent by the representation network, and in absence of the remaining Rs, the generation network basically has to sample to produce reconstructions X prime. And this is what it looks like in practice. So here I'm showing samples or reconstructions from a sequential autoencoder where the number of bits that are being transmitted has been restricted to 76 or so. And the original raw images are more like 25,000 bits. And you can see that if you can only submit 76 bits, what you end up getting are very kind of perhaps abstract or basic shapes and colors. Now, as I increase the number of bits, I get to see more detail and more form and more texture, until at around 220 bits or so, I'm beginning to see object shapes. Like you might see that this looks like a dog and this looks like a human. And at even more bits, you're getting to see very sharp details emerging and effectively the contents of the image. So the idea here was that by going to a sequential autoencoder, we're getting some control over which parts of the representation are more conceptual and which parts are more fine-grained and low-level details. Another way you can modify sequential autoencoders is by putting in interpretability. So we take the sequential autoencoder and then we say that we want each R at each stage to have specific meaning. So we want one part of R to represent the continued presence of another object that needs to be explained, the other part to describe what that object looks like, and the third part to contain information of where it is in the image. So this architecture produces one of these triplets for each object that it encounters, until in the final stage it says, presence is false, I don't detect any new object, and therefore I want to terminate, and the generator produces the final X. So this video shows what that results in. I have an interface here where I'm drawing new digits onto a canvas, and this is the reconstruction produced by the autoencoder on the right. And each time it detects an object, it draws a bounding box around it. And you can see in the bottom, the shape of the autoencoding network actually changes in response to the input image. And this is an example of a case where you have a representation that is changing shape in response to the complexity of the image. Now, another way you can modify the original autoencoding architecture is, for instance, by making the representation 3D in a sense. So in this work, what we did was we took images of a scene. So these two images are of the same scene, and we took the corresponding camera viewpoint that those images were taken from. We passed them through a particular network architecture to produce a vector R, which we call the scene representation. Then this R is passed to a generation network that takes a new camera viewpoint and a randomly sampled Z and produces a reconstruction of what it think it would see had the camera been in that viewpoint. And our hypothesis here is that if we can train the network to do this successfully, then this vector R has necessarily learned the contents of importance in that scene. So it will represent what objects are present, how many objects are present, what colors they have, and where they're placed in the scene. So this is an example of the kind of results that you get. In the top, I'm showing you the observations, these impoverished projections of reality. And in the bottom are the predictions made by a learned generation network. So as I move the camera around, I see that it kind of places the object sensibly. The jittering represents this uncertainty over locations and contents. And you can move the camera either in circles or completely freely, moving in between the objects. So again, the hypothesis is that the only way in which the generator can succeed at this task is if the neural scene representation R has encoded the objects of interest, their positions, their colors, and so on. And note that at no point have we actually provided any human supervision in the form of labels. We've never told it what a sphere is, or what a cylinder is, or what the color blue looks like, and so on. Yet another way that you can represent scenes is shown beautifully in this recent work, NERF, where instead of representing the observation with vector, the representation itself is a neural network. So the representation has weights and biases and an architecture. And the process of producing this representation is actually optimization. So given an input, you run an optimization algorithm to produce a representation that is a neural network. And to get a reconstruction, you do forward propagation through this network to get your reconstruction. Now, this neural network is a much more complex object than just the vector, and therefore it can retain information that would otherwise be lost in a finite length vector. The kinds of samples that you can produce are just remarkable. So these are viewpoints that are synthesized through this neural network with forward propagation. And you can see that the network is capturing complex things like refractions and reflections and lighting and fine object details and so on. Yet another way you can set up the autoencoder is by saying that, I don't want R to be a vector anymore. I want it to be a voxel grid. And so you have your input, you pass it through your representation. You literally get a voxel as your representation, which you can then use to produce the reconstruction. And the benefit of having a voxel representation is that you can then render that object from different viewpoints. Another way you can do it is you might say that I want my representation to be a mesh, not just a voxel grid. Now, to get from a mesh to your reconstruction, that might not be an easy thing to do with a neural network, so we might choose to use software like OpenGL, for instance. And OpenGL, you can approximate the gradients through it with finite differencing. And this is the kind of result that you get. Input image is 2D, representation is a mesh, and then output you can render with OpenGL to get new results. Or you might say that I want to represent my object with an implicit function. And this recent work shows this very beautifully. Input image, you get your representation, and you can use that to render that image from different viewpoints. Now, it's again important to reconsider the fact that inputs are partial observations. So these representation and generation algorithms will have to encode, in some sense, their priors over object shape and content to do these kinds of predictions. Now, everything that I've talked about so far has been likelihood-based, which means that we've been training encoders and decoders so that we maximize the likelihood of the reconstruction or the prediction given the outputs of the generator. But one difficulty that they have is that we have to effectively specify in code what we consider to be a good reconstruction or a good prediction. That notion of similarity turns out to be actually quite difficult to specify. But it's something that you can learn. So with generative adversarial networks, people introduce the concept of a discriminator. So a discriminator is a neural network that takes either inputs of type 0 or type 1, and it's trained to predict whether it's observing a 0 or a 1. So for instance, it might get either real images or images generated by a neural network, and it has to detect if that image is real or if it's generated. And when you train a discriminator in conjunction with a generator like we had before, you end up with a generative adversarial network architecture, or GANs as they're called. So what the GAN does is trying to train a generator that generates good images, and the measure of the quality of those generated images is specified by the discriminator. The discriminator, as I said before, is trying its best to tell between real and fake images, and the generator is trying to fool the discriminator. If you train this well enough, many of you will have already seen these kinds of images. You end up with generations that are remarkably real looking. And this level of fidelity has been shown to be very difficult to achieve with likelihood-based methods, although there's lots of great progress recently. But you will notice that in this architecture, there is no mechanism actually to go from an image X to a representation R. All we have are techniques that go from R to images X. But it turns out that you can get around this with architectures like BiGAN, for instance, and there's other equivalents, where we now combine representation networks, generation networks, and discriminators. And the way you get this to work is by modifying the discriminator so that it's not just looking at the image to detect whether it's real or fake, but it's looking at an image representation pair. So it's trying to identify whether this pair, this R0X0, is real or if it's fake. And if you train this well enough, you can do reconstruction. So you can take this image, for instance, you can represent it to get R, and then you can pass it through the decoder to get your reconstruction. And what the authors here are trying to show is that the learned BiGAN is representing the conceptual features of the image whilst ignoring the perhaps less relevant details. So here, for instance, it kind of knows that it's looking at a farm scene, but it hasn't spent its capacity modeling the details of the grass or the sky. And the hypothesis is that that representation will therefore be useful for, say, scene classification, more so than the raw pixels. Now you can take this even further, combining many of the different components that we've come up with so far. You might say that you want to have a recurrent representation network, a non-differentiable generation algorithm, and you want to make use of discriminators. And the reason you might want to do this is because, for instance, you have a particular program that you want to constrain your generation with. So in this case, we chose a paintbrush simulator like Photoshop, for instance. And the objective was to learn representations that could use this simulator to produce reconstructions of sufficiently high quality. And in advance, we knew several things. One was that the program, the representation network, would have to interact with the program multiple times in order to produce a reconstruction. And that's where the sequential nature of the network comes from. And second is that the simulator simply, there's no way that it will produce pixel perfect images. And so a likelihood-based way of training this might not work. And that's why we use the discriminator. And if you train this well enough, what you end up with are representations that are now physically plausible, at least to the level that is modeled by your paintbrush simulator. So we have an input image. It's now represented as a sequence of strokes that we can send to our simulator to produce the reconstruction, or we can send the exact same sequence of strokes to a simulated robot or even a real robot to produce those reconstructions. Now note that an autoencoder would never be able to do this by default because the representation is a vector, whereas here our representation is more akin to a program. And if you train the same system on, say, human faces, you end up with reconstructions or samples that are actually remarkably similar to how a child or an amateur painter or a cubist painter would draw. So this system has learned to represent faces not as pixel perfect objects, but as a constellation of, two eyes, a nose, lips, and the outline of the face. Now, again, remember that at no point has it ever seen a human painting. At no point has it ever seen how humans paint. It's learned this representation, this fairly abstract representation, because of the architecture of its representation network and its generation algorithm. Now, I want to switch gears and talk about methods that aren't generative at all. So everything we've talked about so far has involved, in some sense, reconstruction of the inputs. But it turns out that you can get away without this. And here's an example of how you could do that. So imagine we start off with a data set of color images, and we deliberately turn them into black and white, monochrome images. And we pass these black and white images through a representation network. And the way we train this representation network is by asking it to produce the colors that should correspond to that image. So for instance, this is a tiger. Tigers have orange fur. So we wanted to predict the orange fur for the tiger and the green for the background. And the hypothesis here is that the only way in which this network can succeed is by first effectively understanding that it's looking at a tiger, even though it won't know the name for a tiger, but the concept of a tiger. And then after that, saying, okay, because of that, I need to predict orange. And the genius here is that at no point do we label things as explicitly tigers or grass. We just give it images and their associated colors, and through that process, it will implicitly learn classification. Or another way of doing this is with rotation prediction. Here's an image, it's upside down, and I want the representation network to predict that it's upside down, and it should be rotated by 180 degrees. Again, the only way it can do this is if it recognizes that this is a tiger, and tigers rarely occur in this configuration, therefore it needs to be rotated by 180 degrees. So this is another example of a task that implicitly coerces the network to learn about concepts that we care about. Now, there are a whole variety of techniques in this space. Some people call it self-supervised learning. I really recommend looking into Andrew Zisserman's slides on this topic that was presented 2 years ago. And there's a whole bunch of papers at CVPR this year as well. But there's one technique in particular that I think warrants further investigation for this tutorial, and that is contrastive learning. The architecture that I'm going to be discussing is the one described in SimClear, which will be presented at ICML this year. It's a simple architecture, and it gets really good performance. So what happens here is we start off with two seed images, a picture of a dog and a picture of a tiger. The picture of the dog we augment twice. And what I mean by augment is we transform it by, say, cropping or flipping or changing the colors. And we also augment the picture of the tiger. So now we have three images, x1, x2, and x3. And we pass each of these images through the same representation network to get R1, R2, and R3. Now, we know that R1 and R2 correspond to the same object because they came from the same image. And we know that R3, because it's coming from a different image, is probably a different object in a different class. So R1 and R2 are considered to be a positive pair of representations. R1 and R3 are considered to be a negative pair, and R2 and R3 are considered to be a negative pair. And all we need to do is we need to say R1 and R2 should be close to each other, so we attract them to each other. And R1 and R3 should repel each other. They should be far away. Similarly with R2 and R3. Okay, so imagine we've done this and we train this. How do we know whether we've succeeded in learning good representations R1, R2, and R3? One way people do this, and it's become a bit of a standard in the field, is with linear separation. So the idea is that after you've done the training that I just described, you freeze the representation network, and then you train a linear network on top of your representation with labels to predict, say, ImageNet classes. So representation network is trained without labels, is frozen. Linear network is trained with labels on ImageNet. And if you do this, you find that a method like SimClear that I just presented ends up getting actually remarkably high performance. So this is 76% top 1 accuracy on ImageNet classification with only a linear network trained with labels on top of the learned representation. And for comparison, I'm also highlighting the BIGAN approach and the rotation prediction approach. To put this in context, the 2012 AlexNet paper, which some would argue sparked the deep learning revolution, only gets, if I remember correctly, in the order of 65% on this task. So we're getting much better than a relatively deep AlexNet network with a single linear network on top of this unsupervised representation. Another way that you can evaluate data efficiency, another way that you can evaluate the representation network is by looking at data efficiency. So here, after unsupervised pre-training, we don't fix the representation network anymore, but we stick another network on top, which is task-specific, and we train it on a task that we care about, but we restrict the number of labels that we give during this supervised training process. So we have the representation network being trained without labels first. Then we fine-tune the representation network along with the task-specific network on a small number of labeled examples. And these are some results that you get from by using something like SimClear. So they're getting 75% top 5 accuracy with only 1% of the ImageNet labels. And this is in opposition to what you would get if you hadn't done pre-training, which is only 48%. So that's almost a 25% percentage point improvement because of unsupervised pre-training. And the third way in which you can evaluate your representation network is by transfer learning. So you do unsupervised pre-training, then you stick on a task-specific network and you train it on something that you haven't seen before. So for instance, you might do Pascal detection. And again, results from SimClear show that this is very, very competitive and in some cases actually outperforms supervised pre-training, for instance, in object detection. Now, finally, I want to talk about the surprising return of likelihood-based models, and in particular, a paper that was released just a few days before this tutorial was recorded, and that's ImageGPT by OpenAI. And the idea here is shockingly simple. So you take your image, you represent it obviously as pixels, but you flatten it down into a vector. So you effectively get rid of all the spatial structure. Then you train big transformer networks on 2 different tasks. One is next pixel prediction on the left, or you do masked pixel prediction, like what people do in natural language processing with BERT. And afterwards, you have a big, deep transformer network, and you can evaluate your ability to do linear classification from each layer of that network. So you have your transformer, you stick a linear network on top of the representation, you freeze the transformer, and you make predictions, say, for ImageNet. And before I show you the results of those linear probes, I want to show you some samples from the model. So this model, if it's trained well enough and for long enough, can produce amazing image completions. given the top half of this image, it produces these beautiful sheep. And given the top half of these birds, it produces the possible completions. So it's very good as a model of pixels, but it's also actually very good in terms of its classification on ImageNet with that linear probe. It's not quite state of the art, but it's competitive, meaning perhaps a return of interest in likelihood-based approaches to representation learning without labels. Okay, I'm going to end it here with a summary. So I hope you will have seen that representation learning is really underspecified. There are many representations that one could come up with for a given image. And there's two broad categories of approaches for dealing with this underspecification. The first is to build in structure, effectively tightening the bottleneck so that you end up with the right representations. And that's what we saw with the structured autoencoders, for instance. The second is to train for proxy tasks that can only be solved if you have the right representations. And that's what we saw with, for instance, contrastive learning or rotation prediction. In my view, current approaches also always seem to involve a trade-off between the generality of the representation, i.e. what range of downstream tasks the representation is good for, and their interpretability. So to what extent we can actually understand the representation by unpacking it and looking at the different variables. So there seems to be a tension between those two things. In my view, general representation learning without labels is still largely unsolved. I don't think anyone has legitimate claim to know how we should be doing this. And that's partly what makes it such an exciting field to be working in. Recent advances, however, are very promising, and I look forward to seeing what people do with this stuff next. Now, in the next part, we will talk about the landscape in a little bit more detail, comparing these different approaches across a bunch of different axes that are important. Thank you. That was the second part of the tutorial. Just a bit of housekeeping. We've got about 15 minutes for Q&A. In the Zoom chat, I've enabled upvoting on the questions and answers, and you can see other people's questions and answers. So I encourage everyone to upvote the ones that they think are more important, because we won't be able to go through all of them. There was also a question on the Slides live chat, which I thought was quite good, which I'll answer. So the question is by Suradeep, and he asks, an example mentioned with the tigers and the cats, the method is not without labels, right? Because you need to know the class labels to train the Siamese type architecture. So actually, it does not make use of labels. So what the method assumes is that if it has two different images, they are probably of a different class. So it doesn't actually make use of the fact that they are, that it's a picture of a dog and a tiger. It just says they're two different images. So likely they are going to belong to different classes, and therefore I will try to repel the representations from each other. You could think of explicitly making use of that labeled information, and there's some papers that are starting to do that. But I agree with you that that wouldn't be considered representation learning without labels anymore. That would be effective. It would be explicitly making use of the labels. Why is the contrastive learning method such as simply or superior to others? Is there any theoretical background? Well, I think it's too early to say that it's definitely superior. I think one of the advantages that it has for sure is that it's not generative, which makes it a little bit easier to work with in research. You can kind of build the architecture without having to worry about the decoder part. You just work with the encoder. And empirically, it does very, very well. But I think the OpenAI image GPT paper came at just the right time to kind of make everyone realize that it's not super clear that contrastive learning is the only way you can do these things. The ImageGPT paper, they get good results as well, empirical results. However, at a huge computational cost. So I think the jury's still out, in my opinion. I'm curious to hear what Irina and Danilo think too.
Oops, I can add some comments. Yes, I agree with Ali said as well. So one other comment about the simpler kind of approach that is different from just density estimation like GPT, or if you use a VE or again from the code, the representation, is that with simpler you also inject more information about the problem than pure density estimation. You're telling the model what kind of invariances you care about. So if you want to classify a cat, you know that if you rotate the cat by 15 degrees, it's still a cat. So if you change some of the details of the texture of the image, it's still going to be a cat. So you know that if you reflect the image, it's still going to be a cat. So there's various invariances that are built into a simpler model, which is external knowledge that you bring into the architecture via this way of training. And this is potentially much more powerful than just blind density estimation as a driving principle for representation learning, because it directly attacks the aspect of the thing that you care about.
Yeah. So this, I recently heard someone refer to this as data engineering. So before we used to do feature engineering, old school machine learning. Before we had deep learning, a lot of time was spent on feature engineering. And then in the past couple of years, there's been a lot of work on architecture engineering, where we've kind of tuned the neural network architectures that we use. And it feels like increasingly we're doing more data engineering of this kind. And I think the consensus in the contrastive learning field recently has been that much of the power of techniques like SimClear and MoCo and CPC is actually, as Danilo says, in the prior information that we put in the data augmentation schemes. They're very powerful ways of communicating to the networks what we think are class invariant transformations of images. So like rotation is class invariant mostly, color changes are mostly class invariant, and so on.
Yeah, just to add to that, I think it also relates to one of the questions on the chat about whether this kind of same representation learning technique should be, in theory, possible to apply to all different sensory modalities. And I think there is a lot of evidence from neuroscience that this should be the case, because the basic architecture and learning rules of the different sensory cortices is pretty much the same. And I think what happens with a lot of these kind of the existing contrastive approaches is that they kind of over specialize to the domain that they're trained on. So, for example, like these transformations that we're building the models to be invariant to might not apply to auditory inputs or other inputs. So maybe one approach, kind of one step forward might be to, rather than have a human engineer the data or kind of create what transformations are applied to the data, we could maybe think about active learning and kind of putting it in sort of reinforcement learning setup where the agent can act in the world and create maybe their data in a more natural way without too many human assumptions. That would be a more general approach.
Great. Okay, so we've got some good questions in the Q&A with upvotes. So continue upvoting, please. So Joao asks, why is linear separation a common evaluation task for representation learning? People have suggested using decision trees. What do you think? So I think linear separation, there's several reasons why it's so common. It's not necessarily the best option, but I'll just go through those reasons in case they're useful. So one is that it's a very simple technique for evaluating a representation. So the idea, as we've discussed, is, for instance, you want your network to learn the concept of cats and dogs, for instance, but it won't actually know to use the name cat and the name dog to refer to those concepts. So the idea with the linear evaluator is to say, okay, I'm going to give it just that amount of information, the transformation from its representation to what we use to refer to that representation. So the transformation from the representation to the label. And in the world of neural networks, you can't get simpler than linear. So that's what people use. Another benefit of a linear network is that it's differentiable. So it allows you to potentially do fine tuning if you wish to do so. So that means that you have two options. One is you keep the representation network frozen and then you stick on a linear and you only train the linear. That's what people typically do in benchmarks. An alternative is you say, I train my network, I stick on the linear, but then I allow the gradients to propagate through the linear into the actual representation network. So that benefit of being differentiable allows you to do this, which might not be possible with things like random forests and decision trees. The point with the linear experiment isn't necessarily to get the best performance possible. It's just to show that something is possible. So in a paper that we did with Olivier Henaf and colleagues, we actually looked at networks that were deeper than linears. And we showed that these networks can be much more data efficient. So we were actually pushing for high accuracy numbers, but with less data. And that was the emphasis. But in the remainder of the tutorial, we're going to talk a lot about evaluation and how classification isn't the only thing, and there's many other actual ways of evaluating representations.
Actually, I would like to add something about on this point. There's a debate kind of in neuroscience about this as well, because for like much of the history of neuroscience, people have been trying to study the representations in the different brain areas by training linear classifiers from the responses of real neurons. But one thing that these approaches kind of miss is that obviously essentially it can't differentiate between different representations that are the same up to linear transformation, right? So they might actually have very different representational form, but if a linear layer cannot differentiate between them, then is it a good thing or is it a bad thing? Like, do we actually care about the fine-grained representational form, or is something that's kind of rotated with a linear transformation okay as well? So I think this is something that we should consider as a field. Kind of, how do we want to evaluate our representations?
Okay, let's move on to the next question. So we have a question from Taiwan who asks about multimodal representation learning. Each modality in this, oh, the question disappeared. Oh, there we go. So each modality will require different encoders because of the data, obviously, of each modality. And this raises issues around data amounts, complexity, size, and how to keep them comparable. What is our opinion on this approach and future directions? So I have to say, I'm not an expert on multimodal representation learning. I know that there's a lot of activity in, for instance, image and audio, or video and audio, or video, audio, and text representation learning. And there's quite a lot of papers on this topic at computer vision conferences like CVPR this year. All I can say is that it feels to me to be a very active area of research, and there's lots of different things being tried. One idea that immediately pops up is this idea of like exploiting cyclic nature of the data to the extent possible. So for instance, you want to be able to arrive at your representation whether you're looking at the video or you're looking at the audio. And if you train explicitly with this, sometimes masking the audio, sometimes masking the video, then your network will have no choice but to make use of all information available. Like, you can't just rely on one stream of information, because sometimes during training that stream just simply isn't present. So that's one idea that comes to mind. But I'm not an expert on this.
So I can add a little bit to Ali's response. So it's true that when we look at different modalities, they kind of carry different kinds of information, maybe different amounts of information. So there's even a saying, like, an image is worth 1,000 words, right? So for example, one thing about language is we typically don't describe things that are kind of obvious or common knowledge. So if we train a model on images and text, it's likely that the text will have less information than the images. So the naive approach of trying to embed everything in the same representational space normally doesn't work, because it's very hard to blend these kind of different kinds of information, different amounts of information. So what people have tried to do, I think there was a paper from DeepMind that just got released, where they kind of embedded things with similar amounts of information, like video and audio, in kind of the same layer, but language was embedded in a kind of like downsampled or like more kind of low dimensionality layer, and then they kind of try to learn another embedding between the two, the kind of the more information, less information. That seemed to work quite well.
Yeah, unfortunately, it looks like we have a message from Slides Live. They say we're a bit behind schedule, and the next part is an hour long. So we're going to close this part of the Q&A and carry on, but we'll be back with questions. And so feel free to continue posting and upvoting until then. I just want to quickly begin by clarifying some questions that were in the chat about contrastive learning. The SimClear method that I briefly put up on the slides, it's important to note that the two images that I showed, the image of the dog and the tiger, we're not making use of the labels. The method just assumes that because they're different images randomly sampled from the data set, that they will belong to different classes. So the assumption is that they will be different classes, and we need to separate them. Another question was, does this stop working when you have fewer labels that you want to care about downstream? It still could work if you just assume that the representation in the unsupervised case, like in SimClear, isn't just about the class of the object, but the fact that the objects are different. So the assumption is that two different images from my data set are probably from two different objects. And I have some transformations of the image, the augmentations, that preserve object identity, and some transformations that don't preserve it, and i.e. sampling different images from the data set. So you still get quite a good learning signal, even if the number of classes are small. But if the number of images is small, then you have problems, because you have very small number of discrete entities that you're dealing with. And then finally, I want to make a note about the fact that data augmentation in these techniques is really important. I heard someone describe it like this. They said that, in the early days of machine learning, we used to do a lot of feature engineering. And then later on, we started doing lots of network engineering. And now we're beginning to put more emphasis on data engineering. So in a technique like SimClear, the particular ways in which data is augmented is precisely how we communicate to the model what we consider to be class-preserving transformations and class-destroying transformations. And that the specific choices of augmentation are very, very important. Okay, so let's go to the chat and see what questions there are to answer. Please upvote the ones that you think are important. Okay, so we have one. Are there any representation learning techniques where the data is not visual or text, but from other sensors such as speed, delay, acceleration, and so on? I'm pretty sure the answer is almost certainly yes. I'm not an expert in this. I mostly work with vision, so I don't have any particular pointers. I don't know if Irina, you know of anything?
Yes, so I think I would agree with Ali that a lot of these models they're developed using typically visual images, just because we have a lot of data sets, we have a lot of benchmarks to compare to, and so you can make controlled progress. And then, of course, these models are applied to other domains, to people who actually use these models for kind of practical applications. But when it comes to research on these other domains, there is kind of quite a few papers that have recently come out that try to essentially learn physics equations from the data. And there you often might have observables that are not, well, almost always they're not pixel images. So these models typically take some sort of like positions and momenta, or like any other basically physical observables, and then try to learn representations for them.
Okay, let's do one more question before we go to the next part, because the next part's a bit long, and then we'll have more time for questions afterwards. So Anonymous asks, he suggested the use of representation learning when an actual object doesn't have a very well-defined shape, size, which can be learned by the model. How do you suggest to learn such representations when the objects do not provide necessary information to the CNNs? I'm not sure I fully understand the question. I'll make a guess. So one question is when the object itself doesn't give you enough information about the properties that you care about. Another question is when you don't know how to represent those properties in a way that will be useful later on. So in the former case, when an object doesn't give you enough information, the wise solution is to maintain uncertainty in your representation. So for instance, if I look at an object and I can't really figure out what its exact shape is, my representation should capture and represent my uncertainty over the shape. So I should say, well, it kind of looks round, but I don't know exactly what it looks like. And that uncertainty will almost certainly be useful downstream for the other tasks that you care about. In the second case, when you don't know how to represent something, then that really becomes a topic of intense research. So many of the things that I talked about in this section were precisely different answers to that question. Maybe you want to represent it with a mesh or a voxel grid or something else. Or maybe it's fully distributed, like the ones that you learn with methods like SimClear. Irina, what do you think?
Yeah, I think I also don't quite get the question. Yeah, I don't think I should have much more to add to your answer.
Okay, so let's just end it here. The next part is a little bit longer, but we'll be back for Q&A either after part 3 or after part 4. Thank you.